Okay, so actually I would like to apologize once again. There was a mistake in the notes. So this is not correct. Yeah, yeah, I was actually wondering also about this, but I went to check and doing the quiz last week, and this is not correct. Yeah, it's I should have noticed that because this is actually more stringent than this. Yeah, so I'm not sure why this was placed here, but yeah, this is not correct. Format ER diagram for assignment 2. Use the Chen's notation. Chen's notation, yeah. So there are two formats that can be used. One is the Close diagram. The other one is the Chen's notation. The Chen's notation is slightly easier to read, so would appreciate if you put it in the Chen's notation. Thank you. Okay, so sorry about that. So because of that, right, last Tuesday's the recording will not be uploaded because got this error. So I don't want you all to listen to the wrong thing. So I'm going to redo this thing again. Sorry about it again. So the condition should be no non-prime attribute is dependent on a proper subset of any candidate key of the table. Okay, so what this means is that if my attribute is a non-prime, it cannot be dependent on the proper subset of any candidate key of the table. So let's say if I have a non-prime that is S, let's say I have non-prime which is S, and my key is A, B. I cannot have A imply S. So this is wrong. Okay. So this looks very, very similar to this condition. But there is a caveat to this. Meaning that if I have two non-primes, T, I can have T imply S. And this will still be in 2NF. So this condition by itself does not cater to this scenario. Yeah. So this is the mistake that was being made. Yeah. So once again, for last week when I shared about 2NF, I only covered one part of it, which is if AB are keys and ST are non-prime attributes, I cannot have a part of a key to imply my non-prime attribute. So this is the partial dependency. This covers this condition, but it is not complete yet. The full condition is that not only can it not it can how to say, it is not fully dependent if on the left hand side it cannot be a part of a candidate key. Okay, it cannot be a subset of a candidate key. So maybe I don't write the double negative. So because it's like the non-prime attributes cannot be dependent on a proper subset of, yeah, I think this one is much better. Non-prime attributes cannot be dependent on the proper subset of anything. Yeah, I think this is much better. Yeah. So non-prime attributes cannot be dependent on the proper subset. So this by itself, right, it will be sufficient already. So this condition by itself is sufficient, meaning that if I have key A, B, I have non-prime to be C, D. I cannot have B imply C because non-prime cannot be dependent on a proper subset of the candidate key. So this will fail the 2NF. But I can have D dependent on C. This will still pass because this is not a proper subset of a candidate key. Okay. Yeah. So please do take note of this. This is the remedy that I'm trying to resolve right now. Thank you. So this example is not in 2NF. So for example, right now I have let's say I have movies T, Y, S, U, A, L. Let's say I have this. So I have TY implies U, U implies A, and ST implies L. So I remember the last time we talked about this, we want to find what is the primary key. The primary key is T, Y, S. TYS seems to be the primary key. So the non-prime attribute, so if let's say to confirm TYS closure equals to TYS U, U implies A, and ST implies L. Yeah, so this is the primary key. So this is the candidate key. So the non-prime will be equals to U, A, and L. So this is a non-prime implying a non-prime. So this is clear. This is part. This passes the 2NF. L is dependent on a subset of the candidate key. So this fails the 2NF. U is also dependent on a subset, and this fails the 2NF. Okay. So I hope this time out I didn't screw up, and I hope this is clearer. Any questions on this? Thank you for your patience. Okay, let's look at the next example. So this is in 2NF. So this is where's my pen? T, Y implies U, U implies A. So let's say I only have these 4 attributes. My primary key in this scenario is T, Y, and my non-prime is going to be U and A. In this case, TY imply U, the non-prime is part of the entire candidate key. So this passes 2NF. In this functional dependency, it is a non-prime dependent on another non-prime. So this also passes 2NF. So this table is in 2NF. Okay. Okay, let's look at the next example. Okay, this example. So I have A, B, C, D, E. A, B, D implies C. B, C implies D. C, D implies E. So yeah, A, B is not on the right side, and I find the candidate key. So these two are the candidate keys. So my prime will be A, B, C, and D. My non-prime will be only equals to E. So this is the non-prime, which is E. It is dependent on a subset of my candidate key, and so this fails 2NF. Okay, let's go back to the definition. Non-prime. Okay, so this one now I'm very sure I can say this. This actually that clears the 2NF. Okay, so CD implies E is the only condition that fails the 2NF because A, B, C, and A, B, D, they are both candidate keys. Okay. Hope this is clearer this time round. So we talked about 2NF. So by right, so last Tuesday when I was sharing, I thought something was a bit off lah, because when I shared last Tuesday, the 2NF condition was actually more strict than the 3NF condition. So I thought, this is very strange. Yeah. So anyway, 3NF implies that every non-prime attribute depends only on the candidate keys or the super keys. Okay. So it must first be in 2NF. Second thing is the non-prime attributes. They depend only on the candidate key or the super key. So this example is not in 3NF. So for instance, Ty implies U, U implies A. Okay, so why is this not in 3NF? Because the key is Ty and non-prime is U and A. U depends on the candidate key, so this is clear. A does not depend on the candidate key. It depends on the another non-prime attribute. So this fails 3NF. Okay. So let's look at one example. A, B, C, D, E. A implies B, A implies C, D, E implies C. So the first thing we want to do is we want to find out what is the candidate key. C implies D. So what are the items not on the right hand side is AE. And from here we know that when the closure of AE is going to give me ABE because of A. It's going to give me ABCE because of A as well. C is going to give me the A, B, C, D, E because of C. So E closure gives me the entire all the attributes. So that is the table. So the prime is A, E. Non-prime is B, C, D. Okay, let's see. This by default is in 1NF, so we have to check whether is it in 2NF or not. So look at the non-prime. Are they a subset of any of my candidate key? So immediately we find that this fails because C non-prime is dependent on the subset. C implies D, E. Again, this also fails. DE implies B. B is here. DE, yeah. So D implies B. So this also fails. And C imply D, or this actually passes 2NF. But however, we know that these are the conditions that fail my 2NF, and so this is only in 1 and okay. Okay, let's look at the next example. Oh, this is the same. Okay, so I was sharing about this. It is always possible to convert a schema to join lossless dependency preserving. Yeah, but sometimes when you create this, the properties may not hold. So for example, I have a table initially of title, year, studio, address. If I were to decompose this into these two tables, I will be losing one functional dependency. Yeah, so that is the issue that we have. In the next form is called BCNF. In BCNF, there's one additional restriction whereby all the functional dependency have a super key left-hand side. Okay, it's actually very strict. To be frank, typically we don't focus. Rather me lah. I usually don't go all the way up to BCNF. Usually, typically 3NF is really good enough for any table. Yeah, so because of that, we only focus up to 3NF in this module. Okay, let's go through some examples. Okay, so A, B, C, D. A depends B, C, D. B, C implies A, D, D implies B. And the keys are A, B, C. So we have prime, A, B, C, non-prime, which is D. Okay, the first thing we want to do is we always check to see, is it first in 2NF or not? So D is over here, and D is fully dependent on a primary key. So D is also over here, and D is also fully dependent on another primary key. So this passes 2NF. Okay. So we check to see 3NF. Does it pass 3NF or not? So in 3NF, let's go through the formula again, the definition. Non-prime attribute dependent only on candidate keys or super keys. Okay, so once again, this is a key. This is a key. So this also passes 3NF. Okay. In BCNF, all the left-hand side must be a super key. A is a super key, BC is a super key, D is not a super key, and so this fails. B, C, and F. Okay. Okay, let's look at the next example. This is the next example. So I have two tables, A, B, C, D, E, F, E, G, F. Okay. So let's look at these as a whole. When we have that, we want to look at what are my candidate keys first. So for relationship 1, A is a candidate key. For relationship 2, E, F, and G, F are candidate keys. So for R2, my prime is my entire E, G, and F. For R1, my prime is my A. Is my A. Okay. So let's check through relationship R2. So for R2, we check to see if is it first in 2NF. So R2 is actually slightly easier because we notice that there's no non-prime. So this is a prime. This is also a prime. So there are no non-prime attributes in R2. So this passes 2NF. Okay. So in let's see if does it pass 3NF or not. So in 3NF, it also passes because E and G, both of them are prime attributes. So it also passes the 3NF. Okay. Then the last thing is we have to check the for the BCNF, we have to check the left-hand side. In this case, the left-hand side is not a super key, and so this is fails B, C, and F. Okay. So this is for R2. Okay, let's look at R1. For R1, it is slightly easier in the sense whereby I only have this one single so-called functional dependency, and so I know that A is a super key, A is a candidate key, and so by default in this scenario, this is in 2NF. This is also in 3NF because all the rest are non-prime and it's dependent on the only candidate key. And this is also in BCNF. So this one actually is a trivial trivial example. Okay. Okay, let's look at the next example. So I have this table A, B, C, D, E, F, G. I have these FDs. The first thing I want to find is the candidate key. So AB is not on the right hand side. A, B, C, D, E, F, G. Okay, so AB is not on the right hand side. If I find AB closure, I will have A, B, C, D. So just for completeness, A, B, C, D, C, D, E because of C, and DE implies F equals to A, B, C, D, E. So AB is the candidate key. So prime is AB. Non-prime attributes are C, D, E, F, G. Okay. So this clears my 2NF. In fact, it also clears my 3NF and even BCNF because this is a super key. How about this? F is a non-prime. It is dependent on two non-primes. So actually, this clears my 2NF. Can you understand why this clears my 2NF? For a 2NF, a non-prime can be dependent on another non-prime. Let's look at this. C implies E. C implies E. Both are non-prime, so this also clears my 2 and F. C implies F. They are both non-prime, so this also clears my 2 and F. And last one, G implies B. G is a non-prime, B is a prime. So, but my key is A, B. So this fails 2 and F because it is a partial dependency. Can? Okay. Yeah. Okay. Let's do. I give you all to try the next example because I think you all try rather than hear me talk the whole night. A, B, C, D, E, F. So A, B implies C, D. D, E implies F. C implies E. And F implies C. So maybe you take the next maybe 5 minutes to find out what normal form is this table in. Have you all done already? Maybe take 1 more minute or so. Okay, maybe I'll just go through this. So the first thing we do is look at the right hand side. AB is not in the right hand side. A, B, C, D, E, F. So I just see whether is it a key. A, B, it is the same example. Oh no, this one don't have this B implies Q. Yeah. So yeah, sorry. Yeah. So this is AB CD equals to AB C D E and A B C D E F. So we confirm AB is the primary key. So these are the conditions that we have. Functional dependency. Okay, so let's look at the first one. So prime is AB, non-prime is C, D, E, F. Okay. So okay, let's look at the first one. AB implies CD. CD is a non-prime. AB is a prime. So this is in 1NF, 2NF, and also 3NF, and actually BCNF. Let's look at this condition. DE implies F. F. DE implies F. So this is non-prime imply non-prime. So this is in 1NF, 2NF. Non-prime imply a non-prime is not a 3NF. So it stop here. C imply E. So again, a non-prime imply non-prime. So it's 1NF, 2NF, and it stops there. And again, this is a non-prime imply non-prime, 1NF, 2NF. So in this table, the highest normal form is 2NF, and this fails the third normal form. Okay, hope you guys managed to get this. So this one. Okay, so this is the next thing we're going to do is we're going to cover something called the Bernstein's algorithm. The Bernstein's algorithm creates your third normal form for you. Okay, so this goes back to our previous lessons on finding the minimal cover, which is why all these are actually very important. So you need to find the minimal cover. You create the new tables from these minimal cover functional dependencies, and then you combine them if you need to. So these are the 3 steps involved. I will go through the example to make it more clear, to make it clearer. Okay, so firstly, I have ABC. I have these two so-called functional dependency. So we check if it is a minimal cover. So this one is quite explicit, implicit. So this one definitely is a minimal cover. So there's nothing I can take away from the left-hand side or right-hand side because they're all singletons, and also cannot remove any functional dependency. So in order to, so this is definitely a minimal cover. So what this is first step. Second step, create a new table. So the new table will then be based on my functional dependency, which looks like this. Okay. So this is second step. Then after that, the third step of combine. Okay. So in this case, right, there's nothing for us to combine. So we will go through some cases whereby we may need to combine some tables. So in this scenario, there's nothing for us to combine. So step 3 is done. Okay. So let's check. Does it preserve dependency or not? So we recall last we went to look at the we went to see how we can add in the alphas. So firstly, the table AB here, and this is AB here, and then we can put in alpha here, and so we have a row full of alphas, and so this preserves dependency. Lossless is also very easy to check because A imply B is over here, B implies C is here. So the functional dependency is part of the table, and so immediately we can say that these are lossless. Okay. Let's look at the next example. So A, B, C, D, E. We first check to see if this is a minimal cover or not. So A implies B, B implies C, D implies C, D implies B, C implies D. So firstly, there is nothing on the left, right that we can take away. So immediately, yeah. So minimal cover. Remember, minimal cover. Step one is to on the right hand side, decompose to singleton. Step two, left hand side, check attributes redundant or not. And step three is to check my FD redundant or not. Okay, so these are the three steps. So okay, assume that we have checked this, and we know that this is the minimum cover. The next thing we want to do is we create the new tables. So from the minimal cover A, we create AB, we create AC, DEC, DEB, and CD. So because of this, we are sure that this preserves all my functional dependency. Because the functional dependency is inside my table. So I'm actually, we are assured that it will definitely preserve all my functional dependency. So the next thing is I want to combine any tables if required. In this scenario, we can combine these two tables. So I have A, B, and C because I have both on my left hand side. So this will come out with this new table. So I can also combine these two tables. DE imply B, DE imply DE implies C, D implies B. I can also combine these two tables. So once I combine these two tables, I realize that I don't need to have another table of CD anymore because CD is already here. Okay. So these are the two tables that are there. So I'm very sure, guaranteed that my functional dependencies are being preserved. The next thing I want to do is I want to check if is it lossless or not. So to check that, we recall again, we have these two tables, P and Q, A, B, C, D, E. By adding the alpha, the distinguished variables, D, E, C, B. Okay. So can you realize that is this? Am I able to make this to be lossless? Let's check. C imply D. Seems to be okay here because of this FD. And let's look at, is there anything that can let me imply E? Doesn't seem to be, doesn't seem to be. So it seems that this table in this case, after I decompose it using the Bernstein's algorithm, it doesn't seem to be lossless, because actually I cannot recreate back my attribute E in this scenario. Okay, so in this case, right, what do we do to make it lossless? So one thing we do is let's find the candidate key first. So let's look for the candidate key of this new table, or rather, sorry, candidate key of the old table here. So I have A imply B. So A is not on my right hand side. B, C, D, E. E is also not on my right hand side. Sorry, right hand side. Yeah. Okay, so it seems that AE will be BC. C will give me D. And so AE is a candidate key. So the way that we can make this to be lossless is that I can add in the candidate key as a new table. So I have a new table PQ. Let's say I have let's say a Q prime, which is A E. If I would add, excuse me, if I would add this as a new table, then I will be able to make this to be a lossless. So this is Q prime. So this is Q prime. We have distinguished variables here. Okay. So once I have this, you notice that I will be able to use this to let me do this again. Yeah. So the reason is because AE is able to imply all the other attributes. Let me clarify this again. AE is able to imply all my other attributes. So you see A implies B. So this will be alpha 1. Using this, A implies C. This will be alpha 2. Then that's the D. Yeah. So C implies D. This will be alpha 3. Is this clear? Okay. I will go through this again after the break. Excuse me. Let's take a quick, maybe 10 minutes break until 9:23. And when we come back, I'll go through this part again on how I managed to get this whole rule of distinguished variables. Thank you. Hello, the time is 9:23 and then we'll start. So the last, before the break, we went through one example, this example whereby we have two tables. One is ABC, the other one is DECB. And we realized that this decomposition actually is lossy. And so the what we end up with is that if it is lossy, what we do is we find out what is the primary key of the original table, and then we add in the primary key as another new table. So the how to say the overall idea is that if you have the primary key as the table, what you need to do is that you can just join everything, and then you will get back the entire table. So definitely you can get back. Okay, so let's do it with the distinguished variables method. So to counter check that the rationale is correct. So okay, we have A as the distinguished variable here. And so we will definitely be able to, we have A imply B. So A imply B. So from this, I will be able to do this. So this is alpha 2. I have A implies C. A implies C. Alpha 3. I'll be able to have alpha 3 here. I have C imply D. And so I will be able to have a alpha 4 here. So I will have a row of distinguished variables. And so this will be lossless. Okay. Hope this is clearer. Okay. So this is just what I mentioned just now. Okay. Now let's look at So this is also what I mentioned earlier. Okay. Let's look at this example now. This example is like very long. So let's do it together. So first, I have AB implies CD, DE implies F, all these conditions. I'm going to assume that this is the minimum cover, okay? So else it will take very long. So I'm going to assume that this is a minimal cover. And from there on, I'm going to create my tables. So AB, CD will be one table. DEF is another table. CE is another table. FC another table. BG another table. Okay, let's see if there's any table that we can combine or not. Actually, for this scenario, there's no table that we can combine. So it's too bad. So we cannot combine any tables in this scenario. So let's check to see if, so definitely this is functional dependency preserving. The other thing is whether is it lossy or not. So I have A, B, C, D, E, F, G over here. Maybe I do it again so that it will be clearer. So A, B, C, D, E, F, G. R1, R2, R3, R4, R5. So I have A, B, C, D, D, E, F, C, E, and F, C, and B, G. So let's check to see if is it a lossless decomposition. Is it lossless decomposition or not? So A, B, actually, see, nothing you can do there. DE, how about DE? DE, nothing you can do. C implies E. Okay, C implies E. I think there's things you can do there. C implies E. Lambda 1. Sorry, lambda 1. Alpha 1. Alpha 1. Okay, so this is it. F implies C. Okay, alpha 2. And B implies G, alpha 3. Okay, is there anything that I missed? Okay, let's check again. AB implies CD. Okay, that's nothing here. DE implies F. There are nothing you can do here. Oh, DE implies F. There's something. DE implies F. Alpha 4. C implies E, nothing. F implies C, nothing more. B implies G, nothing more. Yeah, so this seems to be what we can do. Let me check. Yeah, this seems to be what we can do. So this is actually a lossy decomposition. So if you want to make it lossless, what we do is we just find the primary key of this. We create a new table, and we can prove that this is lossless already. So I don't have it here, but let's quickly do it. So AB is a primary key. AB is a primary, I don't know. AB is not in my left hand side. A, B, C, D. What else is not? E is my left hand side. E, F, G. A, B, C, D. Okay, so let's check if AB is a primary key or not. A, B, C, D. C imply E. And D imply F. Yes, so AB is a primary key. C, DE imply F. DE imply F. Yep. So I will have a table R6, AB, R6. And this will give me alpha here. So alpha, this would, let me change my color. So this is quite trivial, but let's do it quickly. Alpha 2-1, alpha 2-1, alpha 2-1, because of this line. DE implies F. Oh, D implies F, I cannot do anything yet. So C implies E, C implies E, alpha 2-2, alpha 2-2. Okay, then now D E imply F, alpha 2-3, DE imply F, alpha 2-3, and lastly B imply G, alpha 2-4, B imply G, alpha 2-4. So as we discussed earlier, if I were to add a table with my primary key, it will then be able to recreate back my entire table here. Isn't the first row? The first row was filled. Yeah, the first row was filled. Sorry, yeah, I didn't see properly. Yeah, the first row was filled already. Yeah, so I was talking rubbish. Yeah, AB is here. Yeah, AB is here. Yeah, so yeah, first row is filled. Yeah, so actually we don't need this one. Sorry, I missed the first row. Thank you, Jia Wei. Sorry, yeah, bit late. Yeah. Okay, let's move on. Okay. So AB implies CD. So first thing we find the minimum cover, and after that we will combine this to be the table, DEF to be the table, C to be the table, FC to be the table. And what we do right now is, can we combine the tables? Nothing to combine. So yeah, so nothing to combine. So this is fine. The next thing we do is we check to see is it lossy decomposition or not. A, B, C, D, E, F. R1, R2, R3, R4. R1 is A, B, C, D, D, E, F, C, E, F, C. Okay, let's check. A, B implies C, D. Yeah, so this is, I'll be able to fill this one up. D, E implies F, nothing I can do. F implies E. Sorry, C implies E. C implies E. So I will have C implies E. And now I have DE. DE implies F. And so I have the first row of all my distinguished variables. And so this is lossless. Okay. Okay, good. Okay, another example. This is the last example. Okay, so yeah. Then the last example we have is A, B, C, D, E. A, B, C implies C, B, C implies D, C, D implies E. Assume this is the minimum cover. So we create the tables from the minimum cover A, B, C, D, B, C, D, and C, D, E. We can't combine tables in this scenario. B, C, D, B, C, D, B, C, D, we can combine. You don't need this table. A, B, C, D, A, B, C, D, B, C, D. Yeah, we're doing this table. We're doing this table. So we only have two tables actually. Let's check. A, B, C, D, E. R1, R3. So maybe I can have a step 3. A, B, D, C, and C, D, E is R1, R2. So A, B, C, D, C, D, E. C, D implies E. So over here, alpha 1. So this is lossless. A, B, C, D is here, B, C, D is here, D is here. So this is so this is both lossless and functional dependency preserving. So in the end, in this scenario we only need two tables, A, B, C, D and C, D. Okay. Okay, so far. Yeah, if all is fine, very good. Let's go on to the next topic. Next, actually, to the tutorial. Okay. Okay. So maybe you all take maybe about 7 minutes to do this. Maybe 7 minutes. 7 minutes to do this. This may take some time. Yeah. Maybe you all take about 7 minutes to do this. Thank you. maybe I just go through this question first. So I went to rename it for easier. So NCRG. So NC implies G, RC implies G, N implies R implies N. So attributes not in my right hand side is N and C. If I find the closure of N and C, I get wait NCG. So NC implies G, NCGR because of N. So NC is my key, prime candidate key. So I want to find the prime attributes. So prime will be N and C. Non-prime will be G and R. Okay, let's look at this condition one by one. This condition is in this is a non-prime. This is a candidate key. So this is in 2NF and this in 3NF. Okay, let's look at this condition. G RC implies G. G is a non-prime. RC, oh, see, RC is actually part of my so-called candidate key. So actually this is not in, maybe I'll put one in there. Okay. Let's look at R. N is part of my candidate key. So this one will be in 1 and F. And this is a prime. So this one will go to 1NF. It also passes 2NF. It also passes 3NF. So this is a prime key dependent on the non-prime. So this will go all the way to 3NF, but not to BCNF. Okay. So actually in this scenario, this is only at 1NF. RC can also be a candidate key. RC, can RC be a candidate key? Where is RC? Wait, let me see. RC, let's see. Thank you for pointing out. Let's see if RC. Hey, I made a mistake. Sorry. I am making so many mistakes. So, thank you, Jia Wei. So what is not in my left hand side, right hand side? G is only C. So I need to find my C closure, which is it's just C. So I need to find NC closure, which we found earlier is NCRG. As what Jia Wei mentioned, RC is also closure is also NCRG. Let's see, RC closure equals to GRC. Yeah, because yeah. So RC closure is also, let's check again. CG closure is only equals to CG. Okay, so this is fine. Okay, so the prime is N, C, and R. N, C, and R. C and R. My non-prime is only my non-prime is only equals to G. Okay, so let's look at this. So G is in NC, so this is 1NF, 2NF, and also 3NF. And actually NC is a key, so it actually goes up to BC and F. This similarly goes up to BC and F. N implies R. Let me look at N implies R. This is a prime, this is a prime. So this goes up to 3NF. This also goes up to 3NF. Let me see. Yeah, this is a prime, this is a prime. So both of these go up to 3NF. So actually this is already in 3NF. So no further decomposition needs to be done. RC implies G, yeah. So G is RC is a prime, yeah. So it passes Jiawei. So this passes 2NF, it passes 3NF, and actually this also passes BCNF because RC is a primary key. Thank you. So I think there's some bug in this question. So this is already in 3NF form already. Unless I make a mistake. Yeah, I think it seems to be okay. So anyway, I'll check on this, but yeah, seems that this already in BCNF. Oh yeah, it's already in 3NF. Yeah, so I made a mistake. Sorry, thank you. Okay, so yeah, so I made a mistake. So not made a mistake. So I missed out. I missed out one of the candidate keys earlier. So it's already in 3NF because there's no transitive dependency. Okay, thank you. Okay, let's look at the second question. Maybe you take about 5 minutes as well to do this. Hello, I will start. I wrote out the FDs here. Excuse me. Okay, let's find out the attributes that are not on the right hand side. So it's A, B, C, D, E, P, G. So it's only A, B that is not on the right hand side. I need to find the closure A, B, C, D because of this. A, B, C, D, E because of this. And D, E, C, D, E, P because of this. And last one will be B, C, D, E, P, G. So AB is my my candidate key. So my prime is going to be AB, non-prime is going to be C, D, E, P, G. Okay. So let's do this one by one. So a non-prime is dependent on the primary key. So this is definitely 2NF. Actually, this I can immediately put this to BCNF. Immediately I can say this is BCNF. Second one, P is a non-prime, DE is a non-prime, so this is only 2NF. A non-prime that implies a non-prime is maximally only 2NF. Same thing, C implies E, also 2NF. P implies C, also 2NF. B implies G, oh no. So a non-prime is now dependent on the partial of this. So unfortunately, this is only 1NF. Yeah, so this set. So anyway, the next thing we want to do is we want to decompose this to a 3NF. So what we do is we find out if this is the minimum cover. So I think I'm going to assume that this is a minimum. Again, I check the solution. Is this minimum cover or not? Yeah, this is minimum cover. So I don't need to check that. So yeah, but in the exam, please check that this is a minimum cover. Yeah. So right now, because of time, let's not go through that. But during the exam, you need to go through the 3 steps to check that this is a minimum cover. So once this is a minimum cover, the next thing you do is you can carry out the Bernstein's algorithm. So every table will decompose into, or rather every relationship will decompose into a table. So let's see, R1, R2, D, E, P, R3, C, E, R4, P, C, R5, B, G. Okay. So this is the tables we have. There's nothing we can combine over here. So let's check if is it lossless or not. sorry, very messy. R1, R2, R3, R4. Okay, this is A, B, C, D, D, E, P, C, E, P, C, and B, and C. Okay, so let's see if A, B implies C, D, nothing we can do here. D, E implies P, nothing we can do. C implies P, okay? Yeah, quite a lot of things. Alpha 1. Maybe I use, yeah, okay, never mind. Okay, so C implies P, okay. Sorry. C implies E, not P, sorry. Okay. C implies E. C implies, so it's alpha 1, alpha 1. P implies C, alpha 2. P implies C. B implies G, alpha 3. D, E implies P. Yeah. So yes, we proved that this is a lossless decomposition and functional dependency preserving. Okay, so this is how we solve a question like that. So typically you don't need to do this last step unless I ask you. So if I ask show that this is a lossless decomposition, then you need to carry out this final last step. Or like yeah, can. Let's check the answer. Yeah, to see if yeah, so yeah, no combination. Yeah. So this is 3NF, no combination, but and it's also lossless. Okay. Any questions on this? Okay. If all is fine, then we'll go on to the next topic. Still have 10 more minutes, so we go on to the next topic. So remember to mark attendance. So okay. So the next topic is on storage indexing. We have about 7 more minutes to go. But let's do it. Okay, so we already spent so much time on this tonight already, so might as well we use up all the time. Okay, let's do it. Okay, so we review the data storage data on the disk. So records organized in the file. And indexing, we have a primary index, secondary index, B+3, ordered index versus hash index. This will be what lecture 14 will be on. So of course we understand this is the so-called the three so-called forms of storage: primary storage, secondary storage, tertiary storage. This one will be the slowest to get back your data from, then followed by disks, and then followed by primary memory. Okay, so there is this analogy whereby if you, yeah, so the registers the speed that they get into your that can read is like in one minute. So if it's on board cache, it is like the distance is like somewhere in the building. In memory, it's like 1.5 hours, and yeah, so on tape it's like, if you compare within the time, it's like 2,000 years. I really don't know how Jim Wei got this but analogy, but yeah. So anyway, okay, this is the one that I want to talk a little bit on. Okay, this is the old. Of course, this is the, you notice this is the old hard disk. And it's not solid state. So solid state has how to say has index by itself that points to the relevant portion in the memory to read it. Okay, let's not look into the solid state memory first. Let's look at the old type of spinning hard disk memory right now. So in the old spinning hard disk memory, you have something called the disk. Okay, let's look at the disk first. This is the disk. In the disk, there are many tracks. So every single circle here is considered to be one track. One track is divided into multiple sectors, and in every sector there is a single block, and the block has memory of 512 bytes. Okay, so this is just some revision of what a disk memory looks like. Okay, this is the background. How memory is being read from this form of a hard disk, right, is through this setup. You have an arm. This arm will go in, go out to specify which track you want to read from. Okay. Sorry, firstly, maybe not the track first. This arm will first determine which platter you want to read from. So there are multiple platters. So the first thing we do is we want to decide which platter do we want to read from. From the specific platter that you want to read from, then it will spin, or rather then the arm will go in or out to decide which track will you be reading from on the platter. You will then spin towards finding out the sector, and finally read the block from that sector. Okay, so this is how memory is being read from your disk, at least in the past. Okay. Can okay, maybe I go through one last slide. Okay. So the idea that we are trying to do is we want to sort of record, not record, sort of have a conceptual sense of how data is being stored onto hard disk. And we're going to have a few assumptions here, whereby whenever we store data, no record is going to be larger than a block, meaning that all the records are able to fit into the block. Or rather, there will not be a record that is larger than a block. Yeah, there will not be a record that's larger than a block. And so this is one assumption. And the second assumption is that each record is entirely contained within a single block, meaning that this is block 1, block 2. It will not have the scenario of this is record that is passed between two blocks. So these are the two assumptions that we'll have. Okay. So we will continue this in the next lecture. Yeah. So so this part will continue in the next lecture. It's 10:10 already. So I hope don't hold you all back. But